We can continuing now the inyan of Manas govahB Medina, and we explained that it works with solving a spherical triangle. So there is a spherical triangle that we need to solve. Let me get you to the picture. This is the picture of a spherical triangle. Take a look here. Okay, it's clear now. So this is the horizon, Oifik. This is meant, this picture, so somebody that lives very close to the pole, let's say somewhere 60 degrees or 50. Like this is exaggerated, you can see better the calculation. So this guy, this is called the zenith, that's above his head. This line here is called the Oifik, the horizon circle. This is the zenith. This is the North Celestial Pole. Now the distance of the North Celestial Pole from his zenith is 90 minus latitude. That's the rule. So if a guy lives on 60 somewhere in Russia, so the North Celestial Pole is 30 degrees from his zenith. So this angle would be 30. Next, here we have the sun traveling at a certain declination. Let's say it's 20 degrees. So, or any star for that matter. So we want to solve, so this star is reaching here the highest point, culmination it's called, and then it is going all the way till it sets here. When it passes this point, it sets. Now, the celestial equator, we always know it's 90 degrees, because from when it reaches any star that's on the celestial equator, from when it reaches the highest point in the horizon, and here it's 30 degrees, till it sets will always be 6 hours, 90 degrees. So we need to solve this star that has a declination of 20. Yeah, this is 0. This is 20. Doesn't look like 20. Maybe it's 15 or 10. So this has a declination of 15, let's say. Let's assume it's 15. So we want to know how many degrees is this angle. Now, I intentionally did not make a circle here because would not be correct, because we only draw great circles. We never draw a circle that's not great. We cannot do any calculations with it. I just made it to show that the star or the sun is traveling here, and it reaches this point, it sets. So, to solve this angle, a really interesting thing. You see these double lines? These double lines here, they represent this angle. And if you want to understand that, you need to have an actual globe to see why this angle here on top. Again, we take from the North Celestial Pole, we draw a line that is supposed to, it's like a meridian line, we call the longitude line. It goes all the way and it hits the celestial equator. This is a great circle. It goes from the North Celestial Pole to the celestial equator. And then we have this circle here represents the prime meridian. It's where all the stars pass and they reach the highest point, and then they set. So we have this North Celestial Pole, this circle here, the prime meridian, and we will draw a line from the zenith. We will draw it all the way to the horizon. Obviously, it's 90 degrees. Any line from zenith to the horizon, it's a great circle, and it's 90 degrees, obviously, from zenith to the horizon, by definition. And now we have 3 parts of this great circle that are known. Again, zenith to the horizon is 90 degrees. Zenith to North Celestial Pole is 90 minus latitude. In this case, it's 30 degrees. North Celestial Pole to this point is 90 minus the inclination. That is 90 minus 15, 75. Because this here is another 15. So this, from no celestial pole to this point, would be 90 minus 15. So we have already three sides of this triangle that are known. Not the great ABCs, the small ABCs. That is this side, 90 minus, we said it's 75. This is simply 90. And this, it's 30 for somebody that lives in Russia. We need to find, this is the Chiddush here, we need to find this great angle here. This represents this angle here. It's the same. You can only understand this if you have a celestial globe. You'll see that all these circles are parallel to each other. So this circle here, this great angle here, is the same like this angle that this covers from prime meridian till he sets. So we need to find this wide angle. We will call this A, big A. We'll get soon on that nice picture. First, you have to understand what we need to solve and what we know. We know the three small angles. We need to find this wide angle. Now let's go to the other page to see. We took out this thing here. And again, we need to solve this angle here. This side C is called 90 minus latitude. That is the latitude where you would live. That is so this is it's 30. This is 90. This is 90 minus declination, so we said it's 75 because we're talking about a star. So we just took out this spherical triangle. We know A, B, and C. A is 90. B is 90 minus declination, that's 75. And this is 30. We need to find big A. This is called big A. As we said already many times, if you know any three angles, you can find the other three. We need to find the wide A. So we use one of the elementary formulas. That is a formula. That's first formula. It's cosine A is equal to cosine B cosine C plus sine B sine C cosine A. This is the first formula we started off. We do some manipulations. First of all, we know cosine A is 0 because cosine of 90 degrees is 0. So we have 0 is equal to cosine B cosine C. Then we flip the sides. We make sine B sine C cosine A is equal to negative cosine B cosine C. Then we do division. Cosine A is equal to negative cosine B cosine. Then we understand that cosine B is the same like sine of the declination, because B is what's B? B is 90 minus declination. So sine 90 minus that is sine. That's a rule that any sine and cosine you can flip if you do 90 minus that. So instead of writing this cosine B, we can write it as sine declination. The same thing with C. Instead of writing it as cosine C, we can write it sine latitude. So we just use the word latitude instead of C, and we use declination instead of B. And then we get very simple, nice, beautiful way. Negative tangent, because sine over cosine is tangent. So it is, the final result is this. Cosine A is negative tangent declination, tangent latitude. So tangent of 6D in this case. So if we want to know how long it takes for the sun to set when it has a declination of 15, and we're dealing in a place in an area that is at 60 degrees. So if somebody would ask you such a question: how long is the sun outside in such a place? when the sun has a declination of 15 degrees. That is somewhere in the beginning of the summer, like maybe April or May. How long will the sun be outside? So it's very easy to solve. Tangent latitude. Latitude would be, you'll put in tangent, and we'll solve it soon with a calculator here. We have a calculator, and we just do tangent. Latitude is 60, and declination would be negative tangent 15 degrees. These are the two. Latitude is the again is the 15, and I'm sorry, latitude is 60, means on the globe where the guy lives. That's the latitude, means the place where he lives. Tangent 60 and negative tangent 15. And here we'll go to the calculator here. You'll be able to see. Let me make this big. Okay. Okay, so first, this is the. Okay, so I want to show you here. So put this up here. So here you put the expression, and then this is made for Eretz Yisrael. But now I'm going to change it for this negative 0.6 is negative the latitude, so that's negative tangent 15 would make now we will change the whole thing here. Okay, put in here tangent 60. Wow, look how steep this is. I have to bring it into the zone here. Let's see how steep this goes. Get it here to this portion. Take a look here. So again, this is a graph for somebody that lives on 60. That's St. Petersburg. The x-axis represents the declination. So let's say we want to know 15. This is, take a look here. We'll go up to 6, 7. Wow. Pull it up a little bit to reach 15. X is 15. Let's pull it up. Only gets to 13. So look at this. It's 114.99. Let's say 115. That means when x is 13.71, then the declination is we have the sun not even on 15, just on 13.71. We have already a day that's 115 degrees. 115 degrees the sun has to travel from noon. Now it takes for the sun 115 times 4 would be, you can do it on a pen and paper, would be 160. I'm sorry, 660. 660 minutes. 660 minutes. 460 minutes. 460, I'm sorry. So it's another 100 minutes. Another 100 minutes. That's another hour and 20 minutes. And both sides of the day. So it's 2 hours and 40 minutes. That's how much longer the day gets in such areas when the sun is just on 13.71. This graph is not even meant for, because I didn't have to change anyway, you get the picture how this graph works. Now the next thing will explain the Rambam more details how the thing works. how the Manas Goiva Medina works. Thank you very much.